Welcome back. In today's video, we want to go over some basic concepts. These concepts will include current, voltage, and power. So using the universally accepted convention, which states that current is the net flow of positive charge, we can then define electric current as I as the time rate of flow of charge, and that is measured in amperes. So the relationship between current I and the charge Q and the time T is as follow in DC and differential form, alternating. So I is equal to, or current is equal to the charge divided by time. And in differential form, we have the differential of charge Q, differential of time T. Thus, 1 ampere is equal to 1 coulomb per second. And note that there are several types of current because charge can vary with time in several ways. So if current does not change with time, we call that direct current, and we can have a graph to describe what that looks like. So this is going to be current versus time, and current is going to be in amperes, 0 margin mark, and here we have a DC current. So we can make that 2 amperes. So another form is the time varying form, which is normally sinusoidal or alternating current, and that can be described by the same thing. Sorry, not same thing, but a graph. So you're right there. Here we have positive 2 amperes. Here we have negative 2 amperes. So you can see that the current is alternating. It's positive half of a cycle, then it's negative on another half of a cycle. So in general, alternating currents are currents that periodically reverse the direction of current flow. So it flows in the positive, then negative. So voltage, VAB, and we're going to classify our voltage between 2 points, so we're going to call it VAB. An electric circuit is the energy or work, W, which is needed to move a charge Q from A to B, and we'll divide that by the charge. So mathematically, what we're talking about is voltage, and we can at times write it like this, is equal to the work, which is required to move the charge from A to B, divided by that charge. And in differential form, we have the same thing, changing work, changing charge. So voltage or potential difference is the energy required to move 1 coulomb of charge through an element, and that is measured in volts. So the plus and minus sign, let's just use a little diagram. So the plus and the minus sign, let's put that in red. Let's call this B, let's call it A, VAB. So the voltage, the plus and the minus signs are used to define the reference direction or the voltage polarity. So if we take that from there to there, we get a positive voltage. And if we take from here to there, we get a negative voltage. So the voltage VAB can be interpreted in 2 ways. One, point A is at a higher potential, meaning it's positive. Well, it could be positive or it could be lower, but we wouldn't call the higher positive and the lower as negative. So in our case, point A is at a higher potential than point B. And 2, the potential at A with respect to B is VAB. It follows logically that in general, VAB is equal to minus VBA. But I just switched these signs so I can just take it from here. Normally you just take it that way, and you'll get the negative voltage, which is this one. So a brief or a small example of that using the equation for voltage. Here we have the energy required to move a charge through an element. 20 joules, that's the work. 5 millicoulombs of charge through an element. What is the voltage across the element? So basically just using the W over Q relation. That is 20 joules. And that's 5 millicoulomb. And that will give you 4. Well, you move that up top, it becomes positive 3. And that will be volts. So 4 kilovolts. So the voltage required. What is the voltage across the element? So the voltage across the element, if we have 20 joules of energy that is required to move 5 millicoulombs of charge through an element, the voltage produced by that is 4 kilovolts. Power. So power is the time rate of expending, which is using up or giving. So if you expend something, you give it, so you exhaust whatever you have. Or absorbing, which is taking. So expending or absorbing energy, and that is measured in watts. So power is equal to work divided by time. In differential form, we have the differential of work, differential of time. We see that I is the charge divided by time. The voltage is the work divided by charge. So we can write those down over Q for the current, Q over time. So we can then go ahead and simplify the power equation. If we solve our equation here for work and then we solve this for time, we then get that work is Q times V times is Q divided by current I, and this will be equal to, power is equal to V times I. The same way we get that, we could have done this, which we know that V times V is W over Q, and current is Q over T. And we see that the power equation goes back to the same. For the differential form, same thing. P is equal to differential of W, which is work, differential time, and that is equal to V Q. And this is the differential of Q over I, which is equal to V times I. And it checks if we do it the same way as we have done the DC form. So we can see that the power absorbed or supplied by an element is the product of the voltage across the element and the current flowing through that element. So if the power has a positive sign, the power is being delivered to or being absorbed by the element. So go to the diagram again. And positive and negative V, we can make V is equal to 4 volts and current is equal to 3 amperes. So if the power is being delivered to or absorbed by the element I, current is flowing to the element, so it flows in positive direction. Because remember, whenever we draw in a circuit, the way our sign convention is always positive to negative, positive to negative. So in this case, the power is going to equal to 12 watts, and that's positive. Okay, so if the power has a negative sign, the power is being supplied by the element. So the current is flowing out of that element. So in this case, we could say current is flowing that direction, or we can just, either way, you could put it here or you could put it here. Either way. And this I. So thus, P is equal to negative 12 watts. If it's being supplied, we're giving, and if we're giving, so we had 4 apples, and we give away 2. We're supplying 2 to another person, then we're going to leave with 2 apples. So we're giving, we're supplying. So now we would have 2 apples, which is if we give, or if we don't have, if we have and we don't have and we give negative. Anyways, I think you get it, but I like to kind of like use other terminologies to kind of describe it, you know, of giving something. And when you give away, you have negative, because if you have 0 and you give 2, you have negative 2, right? But yeah, it's just a sign convention though. That's why it becomes negative. So maybe trying to use that analogy or terminology to describe it is not plausible. So current direction and voltage polarity plays a major role in determining the sign of the power. So there we go. So when current flows into the element from a higher potential, which if the current flows from a higher potential, positive is higher potential, the element is absorbing power. And when current flows into the element from the lower potential, which is negative, so here negative, so that's why we could have it flowing from here, but it's still flowing there. So it flows from the negative. Then the element is delivering power. So, as always, the law of conservation of energy must be obeyed in electric circuits. So for this reason, the sum or algebraic sum of the power in a circuit at any instance of time must be 0. So again, we can say that negative 12 watts plus that 12 watts is equal to 0. So the law of conservation is obeyed. And that's it for this video. In the next video, we'll be going over some problems using what we just covered. All right, so see you in the next one. Bye.